this colloquium. So he started, his main research area is in string theory, gravity, quantum field theory, fluid dynamics, and many other. He did his PhD from Princeton under Professor Nathan Seiberg. Then he went to Harvard for postdoc as a Harvard Junior Fellow. And then subsequently at the age of 30, he became an assistant professor there. And then after spending few years there, he decided to come back to India, and now he's a professor at Tata Institute of Fundamental Research, Mumbai. He has done several pioneering work, which influence not only my research, a lot of young physicists like me around the world. So some of which include the study of non-commutative field theory, superconformal indices, fluid dynamics, duality between non-supersymmetric field theories, etc., etc., etc. So one of his remarkable works, he showed, probably he might touch upon it, that black hole, which is governed by Einstein theory of relativity, has nothing to do with apparently it has nothing to do with the fluid dynamics, which is governed by Navier-Stokes equation. Full nonlinear Navier-Stokes equation, he showed that can be reproduced from Einstein theory of gravity, which was truly remarkable. His work has been recognized by various awards, which include some of it are ICTV Prize, Infosys Prize, Santi Sarup Bhatnagar Award, New Horizon Physics Award, etc., etc. Okay. Apart from research, he is a truly inspiring teacher as well as a mentor. He has mentored many excellent PhD students and postdocs as well. If you go to, excellent postdocs as well, which was me, by the way. So, if you go to TIFR, one of the things, if you go to DTP, one of the things will struck that there was someone like a black hole, and people are hovering around him, okay? So there will be a cluster of PhD, postdoc, undergrad students always hovering around him. And he'll be continuously talking about physics all the time he's there in the institute. And in this talk, apart from you learn some physics, which is black hole, of course you'll be inspired. But one thing more, I feel like one can learn or get inspired by his amount of enthusiasm or energy to do physics or in general science, which I think is like quite infectious. So I learned a bit, but not much. But hopefully today we'll learn a lot more. Please.
Okay, so thanks a lot, Sachin, for that very over-generous introduction and very affectionate introduction. Thanks a lot. Okay. When Sunil first contacted me and asked me to give a colloquium here, I had planned a slightly more ambitious topic, talking about many details of many things. And then Sunil corrected me and said I had to give something that's very simple. I hope I haven't swung too far the other way. This talk is going to be extremely simple. It's going to have almost no equations. I hope, nonetheless, it will prove interesting. So the topic of my talk here is black holes. And okay, so let's start. The setting of the topic that we're going to discuss, namely black holes, it lies within Einstein's theory of general relativity. Now, as all of you know, a little more than 100 years ago, Einstein developed a new theory of gravity, a new classical theory of gravity that upgraded the earlier theory of Newton. And this upgradation was sort of remarkable in many ways. It was remarkable partly because it didn't just change a few details and make the theory more accurate. It was remarkable because it completely changed the conceptual framework within which a theory of gravity is set. Einstein explained to us that gravity is a quite singular theory. It is a force that has its origins in the fact that matter influences the geometry of space and time itself. Okay? So I've tried to depict this in some sort of cartoon. Imagine you've got some sort of heavy planet or a star or something like that in otherwise flat, empty space. The presence of that planet or star warps space and time, then other things that are moving around this planet or star move around in this warped space and time. And if that warping is not very significant, you can capture that effect by approximately thinking of the effect of that warping as coming from a force, namely the Newtonian force. Okay? Okay. Now, as I've tried to explain here, Einstein's general theory of relativity is an upgradation of Newton's equations. It's an upgradation in the sense that we described. That is, when the warping of space and time is weak, the effect of that warping on other bodies moving around is well captured by associating a force, namely a Newtonian force, acting on the bodies that are moving around. Okay. So Einstein gravity reduces to Newton's theory in some limits. But in other limits, it's very different from the Newtonian theory. And it's different enough so that it predicts entirely new phenomena. One set of phenomena that it predicts that have recently become very famous are gravitational waves. Within Einstein's theory, space and time can ripple in a wave-like way, much like the electromagnetic field ripples in a wave-like way in Maxwell theory. Okay? There's no counterpart of that in Newton's theory. These ripples travel across space-time, much like light travels across space-time. And these ripples, as you know, have been detected in telescopes recently, the telescope LIGO. Okay. So one of the new phenomena that Einstein's theory predicts is gravitational waves. This will not be the main focus of my talk. Okay? There's another sort of qualitatively new kind of thing that Einstein's theory predicts. It predicts the existence of these strange objects called black holes, which is going to be the focus of what I'm going to be, which is going to be the focus of my talk, which is going to be what I'm going to be telling you about. Okay, so what are black holes? So Einstein published his theory of general relativity sometime between 1914 and 1915. And very soon after he published his theory, so his theory was a set of complicated differential equations that describe the dynamics of the geometry of space and time. Very soon after Einstein published his equations, a young physicist, a man named Schwarzschild, wrote a paper describing an exact solution to these equations. Okay, this solution describes a lump. It's a solution that for a space-time that becomes flat, indistinguishable from empty space-time very far away, almost indistinguishable from empty space-time very far away. But as you go nearer and nearer to a central region, which is special in the solution, the space and time starts warping more and more and more. And then there is an inner central region where space-time is extremely, extremely warped. We'll describe that more in 2 minutes. Okay? This new solution, which, as I mentioned, was a solution, an exact solution of Einstein's equations, is now called a black hole. It's a solution describing the dynamics of space and time itself, in the sense that the solution, Einstein's equations have two parts. There's a part describing geometry, and the right-hand side of its equations have some matter. So I told you that matter warps geometry. But we've also discussed that geometry itself can fluctuate like gravitational waves, even without the presence of matter fields. And this solution here is an example of that kind of thing. It's a solution of pure geometry without any matter on the right-hand side. So it's a lump of pure space-time without any matter supporting this warping. Okay. So let's look at this black hole solution a little bit more. As I just tried to say, the black hole solution is a solution describing pure space-time. There's nothing inside of that solution other than space and time itself. Okay? At least outside a certain central singularity where we don't really know what's going on. We'll come back to that singularity in 2 minutes. Outside the singularity, the black hole solution is just space-time itself warped in a funny way that self-consistently solves Einstein's equations. Okay, now this black hole solution here has a very special region. This special region has a name. It's called an event horizon. And the special thing about the event horizon is this. Within the classical theory of general relativity, if you're at a point inside the event horizon, then you cannot get out of it. Nothing can escape from inside the event horizon to go back outside to asymptotic spacetime, no matter how fast it tries to move. You know, the fastest anything can move locally is the speed of light. And even a beam of light that starts out from here, and you attempt to shine it outwards, falls into the black hole. Okay. So the event horizon surface is like a surface of space, a surface of no return. Okay? If you get inside that region of space-time, you're going to end up in the singularity. You'll never be able to make it back outside. Now, this sounds a little weird, so I want to explain this with an analogy. Okay. Imagine you're on a lake. Okay? It's a lake that is with still water, where you know, the edge of the lake is calm and still, nothing much is happening. Okay? However, there's something funny going on in the middle of the lake. There's some sort of sink. Water is disappearing into somewhere, I don't know, to the center of the earth or something like that. So disappearing somewhere. Okay, in the middle of the lake. Okay? Now, because the water is disappearing, as you go nearer to the central point, water is flowing into the center because of conservation of water mass. Okay? So the water is flowing into the center, and when you're very far away, you hardly see this. As you come nearer and nearer and nearer, the water is flowing into the central sink, faster and faster and faster. And, okay. Now imagine that you are moving around on this lake. You've got a motorboat, which has some maximum velocity with respect to still water. Let's say 100 kilometers an hour with respect to still water. Okay. Now, if you're motoring around here and you sort of don't realize that there's this suction region in the middle of the lake, when you're motoring around, you come to the point where the water is moving at 50 kilometers an hour. Then you realize that you're being pulled in. You're not in trouble. You can turn your boat around and accelerate and move outwards. You'll be able to move away because your boat can move with respect to still water faster than the water is moving towards the center. However, suppose let's say that this blue line here is the place where the water in the lake starts moving towards the center at 100 kilometers an hour. Now, if you're inattentive enough to let your boat drift into this region, then there's nothing more you can do. Because even if you turn your boat around and try to move outwards as fast as you can, the water is moving faster than your boat. Water is moving into the center faster than your boat moves with respect to water. And so you'll be pulled in no matter what you do. Though this analogy is far from perfect, it gives you a sense of what happens inside a black hole. The analogy goes that this central region, the sink into which everything is disappearing, is sort of like the singularity. This blue line here is sort of like the event horizon. It's the point of no return. Notice that in this analogy, even though this blue line might be a point of no return, nothing very special is happening here. If you're moving locally along with the water at 100 kilometers an hour, the region of water around you seems like any other lump of water. Something similar, we believe, happens with a black hole. Locally, space-time near the event horizon for a black hole is not different from any other local patch of space-time anywhere else in, say, the patch of space-time in this room. Local measurements don't tell you that you're going through something special when you go through the event horizon, we believe. Okay? However, the way that all these local regions are stitched up into a global geometry makes it that the event horizon is special for some global reason. And the global thing is simply that once you've gone past it, you can never get out. Okay? So, fine. So this is the kind of solution that Schwarzschild produced. Just to recap once more, it was a solution of a lump of pure space-time, not supported except perhaps at the singularity by any other matter. The space-time is warped. It's warped so much that inside a certain central region, separated from the outside by the event horizon, once you get in, you can't move fast enough to get out. Oh, by the way, I should have said, in this particular example here, this blue line depended on the speed of your boat. since your boat had a maximum speed, 100 kilometers an hour, the blue line that was relevant for it was the place where the water was moving at 100 kilometers an hour. But suppose you got a faster boat, one that moved at 200 kilometers an hour. Even if you reached out here, you might be able to get back out. You'd have another blue line relevant to you where the water was moving at 200 kilometers an hour. Okay? However, in the case of the black hole, there aren't many different event horizons, there's just one, because there is a universal speed limit in the world, namely the speed of light. Okay? So, the event horizon can be thought of as the place where not even light rays can escape from the black hole, even if they're trying to escape as fast, as efficiently as they can. Okay. Now, I told you that this strange object emerged not in observations, but in mathematics. It emerged as a solution to Einstein's equations, written down by Schwarzschild. Now, when Einstein and many other physicists looked at the solution, for various reasons, they initially regarded the solution as mathematically correct. Of course, because it was mathematically correct. It solved Einstein's equations. Okay? But physically irrelevant. Einstein many times expressed the view, and even wrote papers saying something like this, that while the black hole solution was mathematically a solution to his equations, it was not relevant for physics for various different reasons. Okay? He offered various reasons for this, but the intuition that seemed to have gone behind his thinking was that it was just too weird. This whole thing was just too weird to represent something real within physics. Okay? And for a long time, Schwarzschild's solution remained a sort of mathematical curiosity, one of the exact solutions of Einstein's equation, but wasn't thought of, I believe, as something in the real world. Now, the next chapter in the story involved an Indian physicist, famous Indian physicist, Subramaniam Chandra Shekar, one of our Nobel Prize winners, who played an important role in the understanding of the subject. Chandra Shekar asked the following question. Okay? Chandra Shekar in the 1930s asked the following question. He asked, suppose you have a star. Okay? What stops a star from collapsing after it runs out of fuel? So, before we get on to trying to answer this question, let's try to put the question in context. Okay. So, imagine you've got a star. The star is a very massive object. Like any other massive object, it self-gravitates. Gravity is trying to pull all the components of the star into its common center. Okay. Now, but if you look at our sun, it's just sitting there, it's not collapsing into its center. Why not? What is the counterbalancing force that's preventing the sun from collapsing into its center? And in the case of our sun, it's easy to work out what that is. And that the counterbalancing force comes from the pressure differentials in the gas in the sun. Okay? The differences in pressure between different layers balance the gravitational force, allowing for an equilibrium solution. Now, these differences in pressure are in the end maintained because there is a constant source of heat in the sun, because the sun is constantly burning hydrogen to give helium, getting a constant source of heat. Okay. Chandra Shekar asked the following question. He asked, well, what happens when this runs out? There's no more heat, so now what's going to balance the inward pull of gravity? Okay. Now, Chandra Shekar proposed that a balancing force for gravity could be found within the quantum theory, which was at that point quite newly invented. And his basic idea went as follows. Look, suppose you've got a box of fermions, let's say electrons. Okay. Now, all of you know that fermions obey Fermi's exclusion principle, which means no two fermions sit in exactly the same state. Now, suppose I take a box of electrons and I ask for the lowest energy state of that electron. That has a certain small momentum. I put one electron in that state. Now I put the next electron in the state, in the box. The lowest momentum state, the lowest energy state is no longer available because the first electron has taken up that state. So the electron goes to the next lowest energy state. You add another electron, it goes to the next lowest energy state, and so on. So if you fill electrons in a box, you get this sort of Fermi sea, okay, where electrons are going to successively higher energy states. Now, so just having electrons in a box has some energy associated with this. There's an energy associated with the configuration of electrons sitting in a box. Now, suppose you try to make that box a little bit smaller. The energy associated with this configuration increases quite rapidly. Why is that? It's because the available energy states are more largely spaced. Because, the first state has momentum approximately 1 over r. R is a measure of the length of the box. Then the next state has momentum approximately 2 over r, and so on. And when you make r smaller and smaller and smaller, all of these energy levels become larger and larger and larger. The spacing between the energy levels goes larger and larger and larger. And so the cost of putting a certain number of electrons into a box is a function of the size of the box, which increases as you make the box smaller. What does that mean in thermodynamics terms? How do you make something smaller? You make something smaller by pushing it or by pressing it. Okay? Because there's increasing energy in making this thing smaller, the system is resisting that push, and so it has an intrinsic pressure associated with it. Okay? This pressure has its origin not in some thermal, not in constantly pumping thermal energy into the system, but just in Fermi's exclusion principle. Okay? Sometimes called degeneracy pressure. There's a certain amount of pressure associated with a box of electrons just from Fermi's exclusion principle. Now, Pauli's exclusion. Some Europeans' exclusion principle. Okay. Now, Chandra Shekar asked, could it be that this degeneracy pressure is sufficient to balance the pull of gravity? Could it be that this pressure is what ultimately stops something from gravitationally imploding on itself once the star runs out of fuel? Now, he did the calculation, okay? It's easy to do a sort of back-of-the-envelope calculation for these things. It's not so easy to get all the numbers right. But roughly he did the calculation and found more or less the following thing. Okay. He found that when the star in question was not too large, in units of the mass of our sun, if the star in question was not too massive, then the degeneracy pressure of the electrons in the star would be enough to balance the gravitational pull. Okay? When that balancing happened, the star would end up in one kind of equilibrium. Okay? That kind of equilibrium, okay, the various names, let's not get into that. When now stars above a certain mass would have a gravitational attraction that was so large that this degeneracy pressure of electrons would not be enough to stabilize it. Now there's a detailed story of how electrons get pushed into the protons, and then they're effectively turning into neutrons. Then over a certain mass, to make any other object of equal or smaller size that would remain static and have the same mass of the black hole. Of course, there are other objects of the same mass. The sun has the same mass as a black hole, of some kind of black hole, but the black hole would be an object, as we said, of radius 3 kilometers, where the sun has a huge radius. I don't even know how many kilometers. Very big. Okay? If you try to squash, maybe you could get more compact stars, but there's no object in the universe that you would be able to make more compact than a black hole with that mass. This is a theoretical result within Einstein's theory of general relativity. Now, black holes are very compact objects, and they're also, in some sense, the simplest objects in the universe. What do I mean by that? Well, take an object like this pointer. It's extremely complicated because it's made up of order 10 to the power 23 atoms. To give a complete description of what's happening in this pointer, you need to specify all of the 10 to the power 23 atoms, what they're doing. That's a very complicated thing. On the other hand, within Einstein's classical theory of general relativity, and we'll be correcting this by the end of the talk, but within Einstein's classical theory of general relativity, Black holes are extremely simple objects because they're not made up of constituents. They're made up of space and time itself, warping in a particular way. And because of that, it's very easy, in some sense, to describe the dynamics of a black hole. Because all you have to do is keep track of the dynamics of space and time itself, and the equations that govern those are very simple, very elegant and clean equations, the equations of Einstein's general relativity. Okay? Another theoretical result is the following. Black holes are dissipative objects. What do I mean by that? Well, suppose you had, let's say, a pendulum without friction. If you set the pendulum moving and there was no friction, it would just keep moving forever. Its solution at late times would be oscillations of any amplitude. Okay? On the other hand, if you had a pendulum with friction, you set the pendulum moving, you can set it moving for a while, but then the friction will damp down its motion, and eventually will settle down to rest. Black holes behave in the same way. Okay? You take a black hole and you give it it has a certain amount of energy. You hit it. The black hole can sort of jiggle around, but this jiggling motion is dissipative. Eventually, the black hole settles down into the state it likes to be in. And the state it likes to be in, like the pendulum, is labeled by very few parameters. The parameters that label a black hole's equilibrium state are its mass and its angular momentum, and that's it. Just some simple conserved charges. Okay? So, we learned three things about black holes. They're the most compact objects in the universe. They also appear to be the simplest because they're made up entirely of space itself, space-time itself, and that equilibrium solutions of black holes are characterized by a few conserved charges. Now, I want to tell you a little bit more about black holes. And within general relativity, one can prove the following theorem. Okay? Using Einstein's equations on the generator of a horizon as manipulated by this man, Amal Kumar Rai Chaudhuri, a famous professor of physics at Presidency College in Calcutta, who's now no more. Okay, the theorems of general relativity that I want to tell you about are these two. The first theorem that uses Rai Chaudhuri's equations to prove is that the area of the event horizon of a black hole in any physical dynamical process can either remain constant or can increase, but can never decrease. Okay? This actually goes hand in hand with the dissipative nature of black hole dynamics. The second theorem, which, and you have to remember, everything I'm telling you about are theorems within classical general relativity. Quantum mechanics can, and in some situations, will invalidate some of these results, but only in weird situations. Okay? So right now we're being classical. Okay. The second theorem I want to tell you about is a theorem that says that within classical general relativity, an event horizon, the topology of an event horizon can never bifurcate, which more simply speaking says that if you've got one black hole, no process within general relativity will allow you to take that and make it two black holes. Okay. Now, if both these theorems are completely correct, what do I mean by if they're correct? They're theorems, so they're correct. Well, they're correct within classical general relativity, but theorems in physics are as good as the assumptions that go into proving them. And sometimes, physically, the assumption fails. So one should always be wary of theorems in physics. But to the extent that these theorems are physically correct, assuming they're physically correct, it means it has an implication. It means that a black hole can never be destroyed, at least classically, without doing something clever and quantum. What do I mean by this? Well, suppose I have an object and you want to destroy it. What does it normally mean? It means break it up into some smithereen of many pieces, right? So let's do this thought experiment. Suppose tomorrow you wake up and you read on in the newspaper that a new satellite put up by ISRO has made a terrible discovery. It realizes that there's a black hole on collision course with the Earth. It's going to hit us in 6 months. What do? Well, maybe Donald Trump will say, let's blast that guy out of the sky. Send the nuclear arsenal. So you'll send a bunch of missiles, they'll go boom, won't work. The black hole will absorb the radiation of the missile and keep going. It'll be a bit bigger. Actually, in such a situation, the only thing you could reasonably do is hope to deflect the black holes. You can't destroy it, but you might deflect it. If it goes and eats Pluto, who cares, right? Okay. 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 That's all I wanted to say about black holes classically. Okay. Now, a lot of research, current research within the theoretical physics community about black holes is not about their classical properties, but about their quantum properties. And in the last 10 minutes or so of this talk, I want to give you a glimpse of what we think we know and what people are trying to understand about black holes quantum mechanically. Okay. So, something that we said right from the beginning of the talk is that black holes are these objects from which things cannot escape. Okay? That's part of their name, black holes. They're black because nothing comes out of them. Okay. Now, in the early 1970s, a then graduate student, Jacob Bekenstein, who's John Wheeler's student in Princeton, began doing various thought experiments about black holes. I don't have the time to tell you about some of these experiments, but by playing around with various experiments, things like, the kind of experiment he had in mind was something like this. Suppose I was in a rocket ship that was going around a black hole, I was drinking a hot cup of tea. This tea carries a lot of entropy. I take this cup of tea and I throw it at the black hole. It looks like the entropy of the universe has decreased. But doesn't the second law of thermodynamics tell me that cannot happen? Okay? These are the kind of experiments he played around with. Okay? And by playing around with these experiments, with these thought experiments, he proposed that black holes would violate the second law of thermodynamics unless the notion of entropy was enlarged to associate an entropy with black holes themselves. And Bekenstein argued that in order to save the second law of entropy, the entropy of the black hole must be proportional to the area of its event horizon. Okay. Now, this proposal, as it's often the case with interesting proposals in physics, was met with skepticism. One of the people who was skeptical about this was Hawking, who felt it was an absurd proposal. Actually, Bekenstein made use of some of Hawking's theorems in classical general relativity to argue for this result. And Hawking, is on record saying he thought it was misuse of his results to come to such an absurd conclusion. And he tried to make precise why he thought this was an absurd conclusion. And he argued as follows. Look, if something has entropy and also carries energy, then we study in elementary thermodynamics that it must carry a temperature. Okay? The formula for the temperature is given by 1 over derivative of entropy with respect to energy. But don't we know that black holes don't carry a temperature? After all, they're black. Anything with a temperature radiates. Black holes don't radiate, so they don't carry a temperature. But when you go through this argument a little more carefully, you find a possible flaw. Because the entropy that Bekenstein wanted to associate with black holes was proportional to the area, but proportional to 1 over Planck's constant, 1 over h bar. Now, the formula for the temperature is 1 over del S by del E, and so the 1 over h bar goes back into the numerator. So if you use this thermodynamic argument to predict the temperature of the black holes, you find that the temperature of the black hole is proportional to h bar. So, if you take this proposal seriously, it implies that black holes have a temperature, not classically, but only quantum mechanically. And then Hawking himself went about, I have some of that here, but okay, let me say it now. Yeah, Hawking himself went around and did a calculation within quantum field theory in the background of a black hole. And much to his surprise, what he found was that when you did quantum mechanics correctly in the background of a black hole, you found that black holes do indeed quantum mechanically keep radiating stuff as if they're at a certain temperature. Okay? So two different kinds of arguments. One motivated by the second law of thermodynamics, and second, which is the second one, which is a beautiful, simple, lovely calculation within quantum field theory, gave basically identical results. Okay. Establishing without any real doubt for a theorist, I think, that black holes should be associated with an entropy. Okay. So now let's look at the entropy again. The entropy of the black hole is proportional to the speed of light cubed, the area of the black hole, by 4g times h bar. This is quite a remarkable formula if you think about it, because it's, in one formula it combines many or all of the most interesting universal constants of nature. There's Planck's constant, there's Newton's constant, there's the speed of light, and there's 4. Okay. Okay. Okay, so, this formula is a formula for area, but for the entropy, it associates a very large amount of entropy to a black hole. For instance, if you work this out for a black hole with solar mass, you find that its entropy is 10 to the power 78. So that the total number of states in such a black hole is e to the power 10 to the power 78. That's a huge number of states. Okay. Now, there are proposals that no object of a particular size can carry more entropy, okay, than a black hole of that same size. Okay? Colloquially, this theorem is often stated as no object in the universe packs more information given volume than a black hole. We've already gone through the material in this transparency. This was about Hawking and his temperature and thermodynamics and so on. So let's move. Let's move. Now, okay, but let me say the following thing. Okay. You see, our classical picture of black holes was as these absorbing and never disappearing objects. If you agree that quantum mechanically black holes radiate, then as they radiate, they lose mass. So the quantum picture of a black hole as something that lives forever is one of something that does not live forever anymore. Okay? You can create a black hole, let's say, by doing something violent, by collapsing a star like Chandra Shekar wanted. And if you had a universe of infinite life, you waited for long enough, that black hole will radiate and radiate and radiate, lose mass, and eventually disappear into nothing. Okay? I think that a solar mass black hole would take a very long time to disappear into nothing. Something like 10 to the 64 years. Okay? The life of the universe is 10 to the 10 is something like 10 to the 10 years. So this is much longer than the life of the universe. But we're not talking about practical things here. We're talking about in principle. In a universe that would live forever, it would eventually evaporate. Also, smaller black holes would evaporate much faster. Okay. Now, this thing about black holes that they can evaporate led Hawking to feel very uncomfortable. Hawking felt that the fact that black holes radiate and evaporate, and also appear to radiate in a very universal way. Okay? The fact that black holes radiate and evaporate in a very universal way seems to be in contradiction with the basic laws of physics, or more precisely, the basic laws of quantum mechanics. In particular feature of the basic laws of quantum mechanics, namely the linearity and in particular unitarity of evolution. Let me explain what I mean. Look, suppose you've got a black hole that collapses because a particular star has run out of fuel. Now, there's a great deal of information. A great deal of information in the particular state of the star before it collapsed. Okay? How much of that star was hydrogen? How much helium? How much boron? What was the distribution of the boron all over the star? You know, all these complicated kinds of things. Once the star collapsed, however, as I have tried to explain to you, it forms a black hole, and that black hole is characterized by very few numbers, just its mass and its angular momentum. So, you might have thought that this process is crazy. It's a process in which you are losing information. All the detailed information of the constituent of the star has gone away into a few numbers. Okay, this might already have made you uncomfortable, but then you might have said, well, you know, perhaps this information is hidden behind the black hole. We can't access it. Okay? But now you can no longer say that if you believe that black holes evaporate and one day go into nothing. So, if information is going to be preserved, it must be that the information of the detailed constituent of the star comes out in the details of the radiation that is emitted as the black hole evaporates. But it's very hard to see how that could happen, consistent with all the usual principles of physics, including locality and causality, because as we've said, the black hole, once a black hole is formed, it settles down into very, very good approximation, at least classically. Okay? It's a very, very good approximation, at least classically. It's characterized by very little information, just a couple of conserved charges. Hawking's calculation and all suggested improvements of Hawking's calculation give you radiation that is determined by these conserved charges, but by nothing else. So within their approximations, at least, the details of the radiation that are emitted carry no information about how much boron there was in the star before it collapsed. Where did that information go? Okay. Hawking proposed that this was a proposal that this was so qualitative, you know, though it wasn't very, very, very precise, it was so qualitatively so far from preserving information that it suggested that black hole physics cannot be consistent with unitarity of quantum mechanics. In fact, this led to a famous bet between Hawking and Preskill, in which Hawking bet that this puzzle, sometimes called the information loss puzzle, would be resolved in favor of black holes. We would conclude that unitarity is not a fundamental principle of nature. It has to be replaced with something else in the black hole context. Preskill, on the other hand, bet that unitarity would win out, that we'd find that there's some sort of flaw in Hawking's argument, and in the end, evaporation of the creation of black hole and production of the creation of black holes and their eventual evaporation would turn out to be a completely unitary process. Now, a few years ago, Hawking famously conceded the bet, telling Preskill he now believes that he's right. He cited some calculations done within the ADS safety correspondence as evidence that he felt, as the thing that helped him change his mind. I have to say that in my mind, the calculations he cited were not terribly convincing, and in my mind, his original paradox, though not very sharp, still to me feels unpleasant. And I think there's a good chance we've not heard the last word on this. So how are we going to clear up these issues? You know, let me say one more thing before I get to this last slide. The last thing is, this. You know, what lies at the heart of the information paradox is two different things I've told you in the talk that are totally different from each other. The first was a classical statement that black holes, when they settle down, are characterized by very few quantum numbers. Their mass and their angular momentum, let's say. The second is that black holes carry a large amount of entropy. You know, so from the first point of view, black holes are extremely simple objects. From the second point of view, they're extremely complicated objects. Because to specify the exact state of the black hole, you have to say which one of those 10 to the power, whatever, you know, which one of those large number of states the black hole actually is in. How can it be true that something carries at the same time so little information classically, but so much information quantum mechanically? In some sense, that lies at the heart of the information paradox in every guise of it. Okay, so how are we going to clear it up? Of course, I don't No one, maybe in the end it'll turn out that it wasn't really a paradox. It's one of these things, right? Sometimes there are some paradoxes in physics which are stated in terms of very concrete equations. You should have got 2, but you got 1. What's the problem? Okay, those paradoxes are almost always useful. Sometimes paradoxes like this one are a bit slippery. It's hard to make into equations. Maybe they will one day just evaporate away. Maybe we'll realize that it wasn't a paradox, but we were just fooling ourselves into thinking it was one. Maybe. But I think it's also possible that, this paradox is telling us something deep about quantum gravity, and that will guide us in our attempts to find consistent theories of quantum gravity. Indeed, a lot of work in string theory over the last 2 or 3 decades has been motivated by trying to understand black holes better, trying to ask microscopically, can we account for the fact that these black holes have so many states? Can we count them within a complete consistent theory of quantum gravity? And then can we use what we've learned from that to try to understand the information puzzle? There's been a great deal of progress, especially in counting by these people, and by the information paradox using the ADS-CFT correspondence invented by Maldacena. But okay, I won't try to tell you more about that. Okay, I'll just end with the statement. The fact that it's proved so difficult to find the mechanism for information transfer suggests that possibly it works in a very non-trivial way. It's possible that the study of black holes will provide the key to open the doors to the next chapter in our efforts to understand the magnificent universe, and in particular the next chapter in our efforts to understand quantum gravity, a subject we're still grappling with. Okay, thank you.